Hello students, I am Dr. Tanmoy Biswas. I welcome you all in my channel Chemistry, the Mystery of Molecules. Today's topic of discussion is oxazole synthesis. You can see the structure. This is one of the 5-member heterocyclic compound with 2 heteroatom. One is oxygen, another is nitrogen. So this is a very interesting molecule. We shall learn mainly about the preparation of this material by 4 reactions. But before going to details, one MCQ. The question is, what is the major product of this reaction? 4 options are provided. I request you student, please pause the video, try by yourself, and whatever answer you get, please write in the comment box. Don't hesitate, it will be right or wrong. Remember, self-evaluation is essential for improvement. Now let's come back to our main topic. So today's content is mainly divided on 4 reactions, or more specifically 4 type of name reaction you can consider. So these 4 reactions we shall learn. First, what is the reaction, and second, the mechanism of each reactions. Okay, so now let's go to the main topic, that is oxazole. So before going to its synthesis, let's learn about the basic idea about this molecule. Its name is oxazole. You may consider oxy or oxa, aza and ol. Oxy means because of this oxygen, aza because of this nitrogen, and finally ol means 5-member ring. So from the name you can understand what could be the expected structure of this molecule. Now this is the patent compound for vast class of heterocyclic aromatic organic compound, and by the way, this topic belongs to heterocyclic compound, or more heterocyclic chemistry, or more specifically 5-member heterocyclic compounds. Now so these are azoles with an oxygen and nitrogen separated by 1 carbon, so carbon number 2. Now oxazoles are aromatic compounds but less than the thiazole, because we know, for example, furan versus thiophene, aromaticity is more for thiophene compared to furan. So like that you may consider. Oxazole is a weak base and conjugate acid has pK 0.08 compared to imidazole. Now question is, why oxazole is weaker than imidazole? So in order to understand that thing, first you need to understand what will happen when oxazole or imidazole will be protonated. So the protonation happens by the lone pair of these 2 nitrogens. Fine. So what happens after the protonation? After the protonation, they will attach to proton and nitrogen will have a positive charge. This is, now this oxazole have a canonical form, means you may consider that the lone pair of this oxygen can push here and it can open. So in this way it will produce, so this is oxygen double bond, this is nitrogen hydrogen, and the oxygen will have the formal positive charge. Similarly, if you come check the canonical form of imidazole, it looks like, so this is the NH, means in this case you may consider that these lone pair will be donated and it will be taken. So you can see this is the double bond, this is the N, this is the H, and there is the positive charge. Now if you check, compare these both, this means canonical form you can consider by a specific term, equivalent canonical form. Okay, so equivalent canonical form, what does this thing mean? It means that the charge, means both are equivalent to canonical form. So you can see these and these both are equivalent, means the positive charge which comes on nitrogen is delocalized over both of the nitrogen, means delocalization means stabilization. So in this case the conjugate acid is more stable. Conjugate acid after protonation is more stable compared to oxazole, because in this case the positive charge is coming on oxygen atom, which is relatively higher electronegative. So if the electronegativity is more, oxygen is reluctant to hold the positive charge on itself. So that's why oxazole is relatively weaker base compared to imidazole. Now let's come back to our main topic, that is Robinson-Gabriel synthesis first. And by the way, this synthesis is involved a 1,2-diketo type, but it is not, this is 1,4-diketo type. So this is 1, this is 4. Why not exactly 1,4-dicarbonyl? Because there is a nitrogen. Okay, so you may consider it's a type, and this could be prepared by Deakin-West reaction. I've already made a dedicated lecture on this topic, you may visit. Now, so these reacts, and actually this is, you may consider actually a dehydration type reaction, I am saying, and ultimate this is aromatic, so aromaticity is a driving force, and in this way this oxazole is produced. So this is the oxazole, and in this context I request student, please recall the synthesis of furan from 1,4-dicarbonyl compound. Not only furan, you can consider furan, pyrrole and thiophene 3. So, and if you have any doubt in this concept, please visit my lecture. I have already discussed in a dedicated video. Now, what is the mechanism associated with this process? First, protonation. So this is the source of acid, means proton. Now student, there are 3 atoms, these 2 oxygens and 1 nitrogen. Now remember, the lone pair of nitrogen is in conjugation with this carbonyl because it's an amide, so that's why nitrogen is relatively less electron rich. So now there is a competition, which carbonyl oxygen will act as a base. Everything possible, means 2 carbonyl can act as a base and get protonated, and remember this protonation is actually a reversible process, but that step will be followed or presented here, which is associated with the final product formation. So that's why I am showing. So here in the first step, the lone pair of oxygen gives to this proton, given to this proton, and it's protonated. Now after protonation, you can see here the carbonyl oxygen became more electron deficient, means activated for nucleophilic attack, and in this context these lone pair of nitrogen of the amide first gives here, and this bond opens and attack here, and ultimately it opens up. So in this way a 5-member ring forms. Why 5-member? Because 1, 2, 3, 4, 5. And if you compare, the oxygen is 1, 2, 3, 4, 5. Now student, whenever there is a chance of ring formation, I request please follow these numbering tricks. It will reduce the chance of mistake. Now this number 2 R3, number 2 R3, number 3 NH, number 4 this R1 and H, R1 and H, and number 5 that is R2. So structure is completely right. Now a question is, why amide oxygen is acting as nucleophile? You can understand this thing by if you compare this ketone versus amide. Now this ketone has a canonical form, you can consider, so it can open and it will produce O minus and carbon will have a plus, and that's why this carbon acting as a electrophile, and this oxygen can act as, you can consider, nucleophile or base. Fine. Now second thing, if you look at this amide, so this is, in this case amide can also have this such kind of canonical form, means this is O minus, this is plus, and this is NH2, but it can have another canonical form, means the lone pair of nitrogen could be donated here, so you can consider that this is the O minus, this is, and this is the NH2 plus, means the electron deficiency on this carbonyl carbon is less, point number 1, but the electron richness of this carbon, means amide carbonyl oxygen, amide oxygen is more. So that's why here the amide oxygen is acting as nucleophile. Now, so this part till now we have understood. So in this case what happens? First see, there is OH and the medium is acidic. So what you can expect, that these OH could be protonated to OH2. So after protonation it becomes a good leaving group. So this is R2, this is R1, and this is H, and this side is R3. Okay, and there is a double bond, this is the protonated nitrogen. So we have understood up to this. Now in the next step, as I told, sorry, this should be one bond. So OH2 became a good leaving group. So what can happen? These lone pair of oxygen can push here and it can leave. Point number 1. So after that you can consider that there is a step, that is N, this is O, this is, and this is hydrogen, and this is R1, this is NH. Student, whenever you draw such kind of structure, please be careful, there is a huge chance of mistake. So I always recommend, please do proper practice. Now See, in the next step you can see this proton, if eliminated or abstracted, then the system will get aromaticity. So consequently it will be abstracted, this bond will come here. So after this oxygen will have positive charge because it gave, so it will come back. So in this way it will produce this canonical form. But till now this nitrogen having positive charge means it is protonated, but final product is not protonated. So after workup the final this oxazole will be produced. And by the way, interesting point is that these R3, R1 and R2, 3 substitution possible, so that is the uniqueness. So this is the first method. Now second, let's come to the second method, which is Fischer oxazole synthesis. And for this purpose this cyanohydrin and aldehyde is used in presence of anhydrous hydrochloric acid. So this is not aqueous HCl, student, this is anhydrous HCl in ether. Now if you look at the source of cyanohydrin, how cyanohydrin is produced? Cyanohydrin is produced from the and separate aldehyde and cyanide. We know because aldehyde can undergo nucleophilic addition reaction in presence of cyanide, which is a good nucleophile. So in this way this addition product cyanohydrin is formed. So cyanohydrin reaction with aldehyde. Now so ultimately it's you may consider it's a complete synthesis of oxazole from aldehyde, or 2 aldehyde you can consider. So how this reaction happens? So first, this is a protonation reaction of anhydrous HCl, please remember. Now in this context, student, I request you please read another name reaction, that is Pinner reaction. I've already uploaded a dedicated video, similar type of concept you can observe. So now, so in this case there are 2 atom, that is oxygen and nitrogen is more electron rich. So in this case it will act as a base and abstract this proton from HCl. So nitrogen will be protonated. So these will be, after protonation it will be converted into this NH plus. Now reaction medium, there is a Cl minus, because this Cl left, this chlorine left. So this chlorine will attack on this carbonyl carbon. So this is actually nucleophilic addition reaction, and such kind of reaction is governed by a concept, Burgi-Tunis trajectory. You may visit this, I have already made a dedicated video. So now, so this means the first step is nothing but, you can consider that addition of HCl to this carbon nitrogen triple bond, means 1 molecule of HCl addition. So it will result in imine chloride, you may consider like that, produced fast. Now in the second stage, see this nitrogen has lone pair 1, so still it can act as a base, and we know base and nucleophile both, we know compared to oxygen, nitrogen is a better nucleophile because it is relatively softer, point number 1. Point number 2, after nucleophilic attack these nitrogen will have a positive charge, since it is relatively lesser electronegative atom compared to oxygen, so it can handle this positive charge efficiently. So after this nitrogen lone pair will attack this carbonyl, or better to say aldehyde carbonyl carbon, and this will open up. So what it will produce? It will produce, this is the R, this part is OH, this part Cl, and this is NH with a positive charge. Now along with that, this is a R double prime, so this is R prime and this is O minus. So you can consider this is actually a charge separated species, means there is a NH plus, so this need to release 1 proton and this O minus need to abstract 1 proton. So proton exchange happen from these 2 sides, and ultimately it will produce a neutral species, that is this one. So you can see this is the product. So this is an addition product. Now fine, in the next step, so 1 OH will be left, means how? See, anhydrous HCl is there in the reaction medium, so these anhydrous HCl will protonate 1 of the OH, and which is more logical? Student, based on my understanding, this part is more logical. Why? Because when it leaves, it will produce a carbocation, and that is relatively more stabilized because these double bond here. So you can say that, sir, this can do the same. It's true, it can do the same, but then the positive charge will come on this nitrogen, which is relatively less favored because nitrogen is relatively more electronegative atom compared to carbon. So positive charge on more electronegative atom is not that much logical. So this will happen in this way, and as an intermediate you can consider that it will produce that this is the OH, this is the R prime, this is Cl, this is N, this is another R double prime, and positive charge is here. So in the next step you can consider that there is a lone pair of electron on oxygen, so it will attack here. So it is actually a ring formation. Ring formation means 1, 2, 3, 4, 5 member ring formation. 1 is oxygen, 2 is, so 1 is oxygen, 2 is R1 you can consider, and 3 is Cl, 4 is nitrogen, and 5 is R double prime. So this one. Now I guess you have understood the overall thing. Now it's a ring formation product, but still it is not oxazole. In the next step, what can possible? See, these lone pair of oxygen can push here. Sorry, I made a mistake. So in the next step, tautomerism possible. So this is actually tautomerism. Means that this proton could be abstracted. It will come here. Okay, and these will be, means this proton abstracted and this will be abstracted proton. So it's a proton exchange. You can consider that this proton will be shifted from here to here. So this is the tautomerism. So this, now in the next step, what you can expect, that it's like a vinylogous system. So it can push, it can come, and it can leave. In this way it will produce the final oxazole. Now a question may come in your mind that, sir, there is one H and there is one HCl. Ultimately this is HCl elimination, but why you didn't show like that? This is H plus abstraction, it will come here, and this is. So student, for such kind of hydrogen chloride elimination, you need this hydrogen and Cl should be in anti orientation, but always we do not have that guarantee that both are anti. They could be seen also, but there is another chance from this oxygen point side, because after this attack it will produce, this is the 5 member ring, this is the nitrogen, this is the oxygen, and here this is the proton, and this is the R prime, and in between this is R double prime. Okay, and these oxygen have positive charge. Now if this hydrogen is abstracted, then system will get aromatic. So it will come, it will go, and it will come. So in this way it will produce, which is relatively more logical, student. So I know if you follow this strategy you will end up the right answer, but in a wrong way. So this is the strategy or mechanism for Fischer oxazole preparation reaction. And in this case you can see these two, this is 2 and 5 positions are substituted. Now let's come to the third, Van Leusen reaction. This reaction is in between a ketone and an isocyanate, okay, in presence of strong base. And so how this reaction happens? This tertiary butoxide is a strong base, so it will abstract the proton. So it abstract the alpha proton of isocyanate and produce this anion. And by the way, this anion is resonance stabilized, because so this is, you may consider, sorry, so this is NC isocyanate, this is the minus, this is the plus. So you can consider that this negative charge could be stabilized by conjugacy. It can come, it can open. So in this way, fine. Now, so this negative charge can act as a nucleophile to carbonyl derivative. So it can attack here and it will open up. Okay, so nucleophilic addition on, you may consider if the aldehyde carbonyl is aldehyde, then this. So first this addition. Second is pretty interesting, that O minus will attack this carbon and this bond will open up. Now a question may come in your mind that, sir, this is C minus, means this is an sp hybridized orbital having lone pairs of electron, means 2 electrons. So how this attack happens when there is a pair of electron? Now student, for that purpose you need to understand a concept, Barghi-Dunich trajectory. Means this is a nucleophile, means the sp3 hybridized orbital of oxygen is acting as a nucleophile. So these orbital need to make a overlap with the pi star of one of the double bond, because there are two pi bonds, so pi star of 1. So for that purpose it need to make an angle, and that angle is generally closer to 107 degrees centigrade. I have already discussed this concept in a dedicated lecture. Now, so this way this oxygen will attack, and this attack is possible, and it will produce a 5-member ring by a 5-endodic pathway. So, and remember student, 5-member ring formation is having the proper conformational orientation. That's why it produces easily. Not only here, in many organic reaction you see 5-member ring formation is very facile. Okay, so after that there will be a negative charge here, because it will attack and one double bond will open up. So from 1 2 means one bond will open up, so from triple bond it will convert a double bond. Fine. Now in the next step is similar, hydrogen tosyl. So similar pathway, just I some last slide I have shown. So it will leave ultimately and produce this anion of oxazole, and later on during the workup it will produce this final oxazole derivative. Now a question may come, why the alpha hydrogen of nitrile is acidic? Similar reason student. So this is a nitrile, and this is, you can consider this is the alpha proton. So if this alpha proton is abstracted, so what it will produce? A carbon ion, and this carbon ion is in conjugation with CN. That's why this is stabilized. Now I request you, please recall the acidity of alpha hydrogen of the carbonyl compound, because from aldol, Claisen, lots of reactions are related to this concept. Now let's come to the last named reaction. I know it's a little long, but student, I want to finish in one lecture. That is oxazole synthesis from α-haloketone. So what happens in this case? These alpha bromoketone react with amine in presence of iodine K2CO3, relatively milder reaction condition, and produces this oxazole derivative. Now what happens here? What is the mechanism? This first step is the reaction of this amine. We know this alpha halocarbonyl derivatives are much more reactive for SN2 type reaction because of the conjugation of this carbonyl group. I have already discussed a dedicated lecture, SN2 on alpha halocarbonyl, you may visit. So it will open up, so it will produce this. Fine. In the next step, what will happen? This iodine in presence of base like K2CO3 will oxidize this benzyl amine derivative into corresponding imine, and in this way you can see this is a conjugated system. So it's stabilization. Iodine is oxidizing this 2 hydrogen, means removal of 2 hydrogen means oxidation. So fine. So here iodine will be reduced into iodide. Fine. In the next step. Now student, please look at this 2 part. So this is 1,3-dicarbonyl type, or better to say carbonyl imine. This is 1, this is 2, this is 3, and we know this 1,3-dicarbonyl derivative or active methylene, they are also named, these protons are significantly acidic. Okay, that's why you can consider that type, you may consider not imine, you can see it's a reverse, but still 2 pi bonds are there, so they are significantly acidic, so they could be deprotonated efficiently, producing a negative charge here. And when this negative charge will be produced, it is resonance stabilized, means it can come here and it will open. So ultimately it will result this thing. And here if you look at little closely, this O minus, it can act as nucleophile, and this is actually an imine, and imine means this carbon act as electrophile. Fine. So what happens here? These O minus do a nucleophilic attack on this and it opens up. It is actually the ring formation. So in this way it will produce this reduced form of oxazole, means there are still 2 hydrogen which need to remove in order to get the aromaticity, and hydrogen removal is oxidation, as I told. So this will done by another equivalent of iodine K2CH3, and in this case iodine is the oxidizing agent, and ultimately it will produce this final oxazole derivative. Now, so I guess you have understood why the alpha bromocarbonyl participate in nucleosubstitution efficiently, because in this case the SN2 reaction is easier due to the orbital overlap between the sigma star and the nucleophile. So now let's come to the MCQ. What is the major product of this reaction? Now student, in this case I shall suggest that let's solve this MCQ in a different strategy. Let's look at the product. What are the options? So all case means there are actually 3 types of protons in oxazole. See, option A, B and C, these protons are abstracted, means so option A means this proton HA, option B means this proton HB, and option C means this proton HC, and final one, nitrogen lone pair of this nitrogen is acting as a nucleophile to react with carbon dioxide, which is a significantly deficient electron deficient molecule. Now, so first step is like a acid base reaction with butyl lithium. Now if you look at this oxazole, which one is more acidic? Because obviously HC is more acidic. Why? Because this carbon atom is in between 2 electronegative heteroatom like nitrogen and oxygen. So since that's why this carbon hydrogen bond is more polar, so butyl lithium, which can act as base, can efficiently abstract this proton, and in this way it will produce the anion, or you may consider the carbon ion of this oxazole. By the way student, one information please remember, that this is question may come that is this anion aromatic or not. If I ask you, is it aromatic? Obviously it is aromatic, because the lone pair, this lone pair is in sp2 hybridized orbital, so that's why you can say that this is aromatic. So during this proton abstraction, aromaticity is not hampered. Now in the next stage, these lone pair of electron will attack, so these lone pair of electron will attack this carbon dioxide and it will open up, so it will produce a carbon dioxide adduct, or means consider the addition product, and later on during the workup it will be converted into this, means initially there will be O minus, after the workup this O minus will go and this will produce OH. So option C is the right answer. Okay, so this is the end of the discussion. Thanks for watching. I request you, if you really enjoy my content, please help this channel to grow, and most importantly I request you please visit my another channel, Climate and Chemistry, where I upload global warming and climate change related videos. So see you in my next video. Bye bye.